as quickly as possible. Okay, let me just say that my plan for today is to go over ensemble learning once more because we had a lot of technical problems last lecture. So I'm going to go over it sort of quickly and then move on to a topic that is one of my favorite. Okay. And I hope it's yours as well. So, ensemble learning. Ensemble learning is about combining many predictors or many models to enhance the performance. Okay? So, it's similar to having multiple people making decision about some important issue versus having just one person. And the general thought is that you make a better decision with multiple people. Okay? So ensemble learning technique is used a lot in machine learning. Okay? And I have a picture here. Rather than having one stick, you have multiple sticks. And multiple sticks is stronger, can be stronger, made to be stronger than one stick. Okay? And today I will be sort of introducing various ensemble learning methods, but I'll be focusing on combining weak learners, which can be thought of as a small stick, a stick that can be broken easily. And you combine many of them to make it stronger than the one strong one. Okay? Let me just read the definition of ensemble learning. Okay. Ensemble learning is a general approach to machine learning that seeks better predictive performance by combining the prediction from multiple distinct models. Okay. And I would like to introduce 3 ensemble methods. The first one is called bagging. The second one is called stacking. The third one is called boosting. In bagging, you sample multiple times from the training data. So you have many training data, and you train it on one type of hypothesis class. Okay. So the here it's written as tree, but you can think of it as just a model. Okay, that's coming from some hypothesis class. Okay, and then you combine the result of each of the models to make your prediction. And if it's classification, you can think of the combined method as taking a majority vote. Okay, so the first model says it's class 2, the first one says class 1, and you find out which class received the most vote, and then you say it's that class. Okay, that will be one way of combining. Okay, that's called bagging. Stacking is you have one training data sample for training different models. Not only different models, but these models can come from different hypotheses class. One is SVM, one is deep learning, the other one, K nearest neighbor, different algorithms. And then you combine that result in some way with another model. And we call that the meta model. Meta model. And you produce your output. The technique that we will be focusing on is called boosting, where you train your model, then you look at the result, and then you train your second model. You look at the combined result, you train your third model, and so forth. Okay? And here in this, it's written as weighted samples. So this will become a little bit clearer as we talk about ADA boosting in more detail. But not only weighted samples, it's written as weighted sample, meaning that samples that were misclassified or samples that were difficult to classify, that would get more weight, and samples that were classified easily or correctly each time, the weight will be reduced. Okay, so in boosting, one of the characteristics is to have a distribution over the sample data. You have a distribution, okay? And this distribution or this weight tells you how difficult it is to classify or predict the label of these data, okay? And we will be focusing on boosting. And we'll be focusing on one particular algorithm called ADA boosting. And just to say a little bit more about the third method, boosting, it constructs a highly accurate nonlinear classifier of voting or averaging an ensemble of very simple and weak classifiers. So the key point here is in boosting, you sequentially pick out or make models, and these models are weak models or simple models. And I'll define what I mean by weak and simple classifiers. Okay? And the base classifier only needs to perform slightly. So the base classifier here means as it's picking out the classifiers sequentially or at each round, it's becoming stronger and stronger, or the performance is going to improve, but each of these classifiers will be slightly better than tossing of the coin, slightly better than random guessing. Tossing of the coin, random guessing. Okay? And this is the mechanism. You train multiple weak classifiers, and at each turn, you identify misclassified samples, okay, and you train a new one to do well on the weighted sample set. And I mentioned that if it's more difficult, then the weight will be higher. And you continue this thing sequentially. The method that I'm going to talk about or focus on was developed by Freud and Shapiro, okay, who was working for AT&T, a telephone company, and they wanted to classify the calls, okay? And that algorithm, ADA boosting algorithm, won the Gödel Prize, okay? And in 2003. And this method is used not only for classification, but various other tasks, okay? There is, in fact, a book on ADA boosting. Okay, if you're interested in this method, please send me email, okay? Okay, weak classifier or weak learnability. Weak learnability is when the test error is bounded above by some number that is slightly less than 0.5. Okay? And I'd just like to remind you that we are talking about binary classification here. Binary classification. Okay? So the test error being equal to half is random guessing. But if I minus some gamma value being greater than 0, that is a little bit better than tossing of the coin. Okay. And strong learnability is something a little bit different. It's upper bounded by epsilon, and epsilon is any value that you want. It's just something greater than 0. Okay? So for any distribution, a concept class is strongly learnable if and only if C is weakly learnable. And there's, okay? So let me just tell you how ADA boosting works. You're given a data, training data with data and label. You have n number of them. And the label is assumed to be -1 or 1. Okay? It's just a choice. You can make it 0 and 1, or you can make it -1 and 1. You can make it -10 and 10. Okay? But here, -1 and 1. And I have a hypothesis class full of weak classifiers. Okay? In fact, there are L number of weak classifiers in this hypothesis class. Okay? And that's denoted by GK here. And it outputs -1 or 1. And boosting, through boosting, we're going to pick one hypothesis class at each round. We call it round. So at G t equal 1, T1, you will pick out one of the classifiers from the L possible classifiers. And you're going to go through T rounds. And your final classifier will be a linear sum of the weak classifiers. Alpha T is something that will be evaluated during the rounds. And your final classifier would take the sign of the combined classifiers. Okay, so it gives you +1 or -1 because the sign is going to be +1 -1. Okay? And in boosting, it's different from other ensemble methods in that we have a weight distribution on the training data. So we are assuming there are n training data. And initially, each one will get the same weight. The weights are assigned such that when you add up the weights, it equals to 1. So this is what goes on. So we're going to go through the rounds. Round 1 to round T. And you want to pick out a weak classifier from the hypothesis class, which contains L possible weak classifiers. You want to pick one that's going to minimize this weighted error. So initially, the weights of each of the data was equal, n/1. And this represents an indicator function. Its value 1 when the argument is true. When it's false, it takes the value 0. So when your prediction is not the same as ground truth, you get a value 1. That's an error. So you pick out or you select a G, a weak classifier that minimizes that error. Okay? And alpha T is, which is the weight that you place on the weak classifier when you're combining, is given by this equation right here. And I'm going to sort of derive why this is true, or I'm going to sketch a derivation why this is true. A half natural log epsilon t, 1 minus epsilon t. And I mentioned that epsilon t is going to be slightly less than a half. That's the error. So this is slightly less than a half. This one is slightly bigger than a half. This value is going to be greater than 1. So alpha t is going to be a positive number. So the weight that you place on the weak classifier is going to be positive. After you found the weight, after you found the classifier and the weight associated with that classifier, you're going to update the weight of the data. So this is the weight of the ith data at time t. And it's going to be updated by this quantity here, where yi times g, when your prediction is aligned with ground truth, this value is going to be +1, positive number. This is a positive number. And you have a negative exponential, which means that you're going to have a value less than 1. So you're going to downweight. If you correctly classified the ith data, the weight, the updated weight is going to be downgraded. Okay. And vice versa. If it's incorrect, then it's going to raise the weight. ZT, what is ZT? ZT is a normalizing constant so that when you add up the weights for all the training data, it equals to 1. Okay? So here is a toy example of pluses and minuses, okay? And the size of the data represents the weight that is placed on the data. And the hypotheses class are vertical or horizontal half planes. So in this toy example, there are infinite number of hypotheses. Okay? So it's either horizontal or vertical. And you start out with all the data having equal weight. So here is the first classifier. The red one represents. And you see that it made 3 errors. So the error is 0.3. And once you have the error, you can also calculate the weight that you place on the first classifier. Then you update the weight on each of the data. And you can see that the misclassified data for its weight has been is bigger, and the weights of data that has been classified correctly has been reduced. Oops. 정말. 알아보라고 나. 이게 노트북이고. 노트북은 어떻게 돼? 안 되네. Okay. So G1 was the best weak classifier. We found the error, the weight, updated the weight on the data. Then we find that G2 minimizes the weighted error, and it's another vertical classifier. We can find out the weighted error, and we can also find out the weight of G2. And then we again update the weight of the data. Okay, so these three, the red ones, small red ones, have been misclassified, so their weight has been increased, while the other ones have been reduced. This one was misclassified first time, but it's classified correctly the second one, so the size has been reduced. Again, G3, now it's a horizontal classifier. You find out the error. You also can find out the weight. And after going through 3 rounds, okay, finding the weak classifiers, okay, and you're combining them and you're taking the sign. So the blue area represents the positive, and the pink area represents the negative, okay, for this classifier. So let's try to do some analysis on this, okay? Now, it's going to turn out that the training error on this hypothesis class is upper bounded by this quantity here, okay? And this upper quantity can be by manipulation, can be written in this form, and this term is upper bounded by the exponential of this term. This is an important fact because it tells you something. Can someone tell me, looking at this, what this is saying? And if you give it a try, I will give you some chocolate. What is this slide saying, actually? Actually, what is this saying? No chocolate? No chocolate before lunch? Okay, let me just tell you. So it's upper bounded by some exponential. Okay, and these are positive. So as the round goes up, this is going to be more negative. Exponential of a negative is dropping very quickly. So the training error is dropping very quickly. Which is good, right? Okay. Now let me sketch the proof. Sketch how this was arrived. Here's a definition of the weight update. Initially, it was, when the first round, all of the data had n over 1. And we can sort of unroll this recursively. So big T plus 1 of the ith data will have this. This is I equals 1. This is I equals 2. This is T equal 1, T equal 2, T equal 3, and that is T equal big T. Okay? So you get that. You can combine that to get this. Okay? And we said that this was going to be defined as Ft. We call that Ft. Where is it? Yeah, we call that Ft. Okay? And in the second step, the training error is going to be the average of the loss of all the training data. And the loss happens when yi and this ft is negative. Then we know that they are in disagreement. This will say maybe +1, and this will be negative something. So it will have a different sign. Okay? Now we can also see that this I is upper bounded by the exponential. Okay, how do we know this? We know that if this is equal to 0, then exponential of 0 equals 1, right? So they're the same. If this is positive, then what happens to this? If this is positive, then this is 0, and exponential of this positive, so the exponential is going to be always greater than 0. Okay? Now when this is negative, okay, and this, if it's negative, this value is going to be 1, right? Exponential of a negative of this, which is negative, so you got a negative and a negative, that's a positive. Exponential of a positive is always going to be greater than 1. So this is going to be always be greater than that. Okay, for all cases. So now, rewrite this f of t. We can here, f of t, we can make this thing the subject by putting this on to the right-hand side, to the left-hand side, And what we get, so this exponential of that will be WT plus 1 I times N times this. You have that. You could take the sum of, this is sum over I. There's only this term. This term is only a sum over I, and the others are not, so you could just, the N cancels out, and you could do this thing separately. This value, for all training samples, if you take the weight of all the training samples, we said that it's going to be equal to 1. That's how our weights was defined. So this is going to equal that. So the training error is going to be the product of the normalizing factors. Now, ZT is defined by this, okay, which was the normal, that's how the normalizing factor was defined. Here's ZT. Okay, this is normalizing factor. So ZT is equal to that. We can separate this thing into two terms. The term where Y, I, and this prediction are in disagreement, and also a term where they are in agreement. By the way, GK outputs a value 1 or minus 1. Okay, so it's here they are in disagreement, so this value is minus, so we're going to minus and minus, that's alpha t. Here they are in agreement, so you get a negative term right here like that. So this is the error. We're going to have the error times e to the alpha t. And here, it's 1 minus the error times e to the minus ft. Okay. So we want to find alpha t that minimizes this thing. I want to find my alpha t that minimizes that. And we find that the alpha t has to equal that. Okay? And substituting alpha t back to zt gives that. Okay? The training error is bounded above by the product of z to the m, where we found this. Okay? And we can say that the training error can be driven to 0 if the weak learners are sufficiently strong. Okay, so we can drive this and make this thing equal to 0. And if gamma m is lower bounded by gamma, some gamma, and it's not, it's just a minimum value of all the m's, okay, then the training error drops strictly to 0 after this many rounds. Okay. And typically the test error is bounded above by the training error and this order of this term. If you look at your previous lecture note, it's going to be here D represents the VC dimension. Gamma, 1 minus gamma is the confidence level. N is the training data in this case. Okay. So this is the VC dimension that you would get. And by the way, T here is the number of iterations or number of rounds. So what is this saying? This is saying that if the iteration goes up, then this value is going to go up. So our prediction on the test data, on the test error, is not going to be accurate, because as this goes up, as t goes up, this thing goes up. But we find that this is not the case. Well, this would seem that as you go many more rounds, selecting more weak classifiers, you're going to be worse. But this is what happens actually. So here is a graph where this represents iterations or rounds. In ADA boosting, it's called rounds. Okay. And for training error, it's going down very quickly, exponential. And this is what we would expect for the test data. For data it hasn't seen, we would expect that it will drop and then grow. This is generally what we would expect. Okay? But this is what we observe. Here is the x-axis. Here is the rounds, number of rounds. And y represents the error. The training error goes down very quickly. And after maybe 3 or 4 iterations, the error is 0. And the test error just drops and never rises. And what's particularly interesting is that even though you reached 0 training error and you keep on iterating, the test error starts to go down. The training error is 0 after, 3 iterations, and you keep on iterating, the test error goes down. Even though you reach training error equal to 0. And this is what we also observe. The x-axis represents the margin. Okay, and I'm going to tell you what the margin is, how margin is defined here. And y represents the accumulated distribution, number of samples. Okay. Now you see that, and the green represents the iteration. So after 5 iterations, 5 rounds, you observe this type of thing. And this is saying that the margin is, generally we would like large margin. The margin that is defined for this is the number of training data that was incorrectly predicted versus the number of correctly predicted. So it's the difference between the numbers. Okay? So out of the 100 data, let's say 60 was correctly and 40 was incorrect. Then the margin is 20. Okay? And you somehow normalize it. And that number, if I get more error then more correct, then it will be on this side. And if I had more correct, then it will be on this side. Okay, did that make sense? This is 5. That's 100 and 1,000. So we see that most of the samples are, have margin very, very large. Okay, as you go more iteration, the margin becomes larger, meaning that there will be more correct than incorrect. Okay. So here it is. Correct and incorrect is the difference. So what this is saying is, as you go through more iterations, 5 iterations, the difference between the correct and the incorrect becomes greater. So you're getting more. And in fact, the generalization bound becomes this. The test error is bounded above by the fraction of training samples with margin less than theta. Okay, so this represents sort of like the training error. If it's not above, if the margin is not above theta, then that's sort of like saying that you have an error. Okay, fraction of training samples with margin less than theta. And this interval here. And the interval here is d divided by theta, the theta squared. So t times the VC dimension is gone in this formulation. Okay? So as you increase this value of theta, by the way, the margin is weighted fraction of the correct minus the weighted fraction of incorrect. Okay, so it's similar to what I just said. But weighted fraction of the correct and weighted fraction of incorrect. And it turns out, if I make theta sort of represents the margin, if theta increases, then this interval goes down. Okay. So even though the size of the final classifier is getting larger, t being greater, we were worried that if t got greater, then the interval would be bigger. Eta boosting pushes the margin, theta, to be larger. And the complexity penalty depends on this rather than this. Okay. Okay. The advantage of eta boosting, it's fast to execute because it's summation of weak classifiers, very easy to program. There is no hyperparameters. Okay, there's no tuning. You just the alpha t's and what is it? Alpha t's can be evaluated. It's no hyper tuning, and it can wrap around any base learning algorithm. You could use different models. Decision tree. I don't know if you're linear model, various models you can use as the hypothesis class. No prior knowledge is required. Okay, and the goal transitions from finding a highly accurate model to merely finding rule of thumb that are barely better than random guessing. Okay, and it can do multi classification. Bagging and boosting, that's better. Okay, so that's ensemble learning. Okay, any questions with regards to this? Okay, if there's no question, then I'm going to move on to graphical models. So the graphical model that I'm going to be talking about is probabilistic graphical model. So the graph is going to represent the probability. Okay. Now, I don't know about you, but for me, probability has been very, very difficult because it's all equations. But with probabilistic graph models, you can quickly see insight into various probabilistic tasks. Okay. There are many different types of graphical models, and I'm going to be talking about only two, directed and undirected graph. The one that is predominantly used right now is called factor graph. Okay, and I'm going to leave that out. So let me just explain. So probabilistic graph models combines probability theory and graph theory. Okay, and it allows you to visualize the probabilistic model, and with this, by being able to visualize the probabilistic model, it gives you insight to designing a new model. And the property that is most important when you deal with a graphical model is conditional independence. Okay, you need to understand conditional independence. And computationally wise, by it being able to visualize, you can reduce the computation. It will give you insight into reducing the computation. Okay. So the probability theory that you needed to know for understanding probabilistic graphical models, only these. If you have a joint probability and you marginalize over one of the random variable, you get a marginal probability of the other variable, right? I'm showing you all of this in with two random variable, but this can be generalized to multi-random variable. Okay, so I'm marginalizing. This is what we say, marginalizing over one of the random variable leads to a marginal probability of the other. Okay? The product rule. The joint probability of x and y is equal to the conditional probability of x given y times the marginal probability of the other variable. Okay? And we are all familiar with Bayes' rule. Okay? Bayes' rule is very, very important in machine learning. The conditional probability of y given x is equal to the conditional probability of x given y times the marginal probability of y divided by the marginal probability of px. And px, this thing, is sort of like the normalizing factor of the numerator. I mean, if you understand these three rules, or two rules and theorem, you'll be all right. Okay? So, this is probability. Graph. I'm going to represent all of this by a graph. Graph consists of nodes and edges. Okay? The nodes are going to represent the random variable. Okay? The nodes represent the random variable, and the edge represents the probabilistic relationship between the two random variables. Okay? And there are two different graphs that I'm going to be talking about. Directed graph or undirected graph. Directed graph is sometimes called the Bayesian net. Okay? Directed graph. Undirected graph is sometimes called the Markov random field, MRF. Okay? And there is factor graphs, and if we have time, we'll talk about it. So let me first introduce directed graph, okay? And it's sometimes called the Bayesian net. So here is I should like to just say that directed graph and undirected graph are different in that the edges in the directed graph are arrows. So you have arrow leading from one of the node to another node. In undirected graph, which is sometimes called the Markov random field, there is no direction. It's not an arrow, but it's just a line. Okay? So here is an example of a directed graph, okay, involving three random variables, x1, x2, and x3. And the edges have arrows. It's going from one to the other. Okay. This directed graph represents the probability, the joint probability of all the random variables in the graph. So what is this? This represents probability of x1, x2, and x3. Okay, this graph. Now, I'm going to tell you what these edges mean. The edges represents the conditional probability. So this arrow represents the conditional probability of x2 given x1. There are two arrows leading to x3. These two arrows leading to that represents the conditional probability of x3 given x1 and x2. x1 has no arrows coming into x1. So it's that is represented as probability of x1 given nothing. So that's equal to probability of x1. Okay? So the joint, and I said that this whole thing represents the joint probability of all the random variables in the graph, probability of x1, x2, and x3, which is equal to the conditional probability of each of the nodes. So x1, there were no arrows coming in. So the joint probability is equal to probability of x1 times conditional probability of x2 given x1 times the conditional probability of x3 given x1 and x2. Okay? So this can be generalized. So the joint probability of all the random variables in the graph is equal to the product of the conditional probability of each of the random variables given the parent of xi. What is a parent of xi? Let me demonstrate by example. Parent of x2 is x1. Parent of x3 is x1 and x2. Okay? So as I said, that this represents the joint probability of x1, x2, and x3, and it's the product of the conditional probability of each of the random variables given the parent. x1 does not have any parent, so it's just px1. x2 has just one parent, x1, and x3 has parent x1 and x2. And it's the product of those two. That's represented by that. Okay? Now, it turns out that the absence of link, absence of these edges provide more information than the link, presence of link. Okay? And I'll make, so here is an example of the grade that you will receive in this course. Okay? The grade that you receive is going to be a random variable. It's probabilistic. And it's going to be dependent on the score of your exam, your intelligence, It's going to depend on the difficulty of the course. It's going to also depend on the time that you put in this course and also how many questions you ask. Okay, these are the factors that's going to determine your grade. Now, let me just explain this. I mean, in all machine learning problems, you have a goal of trying to infer a value. Okay, so you're trying to infer the label. Okay, that label, and if you can come up with, if you can think of all the variables that's going to affect your outcome, your label, and you can draw a graph like this, then that task will be much, much easier. Okay? Very few researchers attack their problem, solve their problem in this manner. But this is very, very important. So you have a label that you want, and you have to think about all the factors that's going to affect your label. Now, let me just give you an example of this. We're going to start out with your intelligence, okay? You're born with some intelligence. That's a random variable, okay? Your parents. And depending on your intelligence, you're going to spend more or less time. If you're really, really smart, you're going to spend less time. If you're less intelligent, then you're going to spend more time. And your score on the exam will depend on the difficulty. The lecturer, me, when he's making the exam, or the TAs are making the exam, and they're in great mood to help you, that's probabilistic. Then the difficulty might go down, but they're in bad mood, then they may make it really difficult. So the exam score will depend on probabilistic conditioning of the staff here. It would also depend on how much time you spent on this course. It's also going to depend on how much questions you asked in this class. Well, if you asked a lot of questions and they're resolved, that means that you're going to do well. If you don't, then... So these are the three factors that's going to also directly determine the score of your class, of your exam. But the score of your exam is influencing your grade, but it's not the only thing. You got projects and homework, okay? And depending on how well you do that, so the score of your exam is going to affect your grade, but it's not deterministic. It's going to be probabilistic. Now, you can make all of this thing into a binary term. Intelligence, low intelligence, high intelligence. Difficulty, easy, difficult. Time, less time, lots of time. Question, no asked, no question, asked question. Score, you can get unsatisfactory score, satisfactory score. Your grade, satisfactory, unsatisfactory, satisfactory. All the random variables, you can say, define it as binary. And then to define these edges, you have to come up with the probability. So intelligence is binary, okay? You're going to start with some binary. And then from intelligence to time you spent, the probability of time given intelligence. So how many marginal probabilities do we need to determine this? So what I'm saying is you are not intelligent and you spend a lot of time. You're not intelligent, you spend a lot of time. You're intelligent and you spend a lot of time. You're intelligent and not spend a lot of time. There are 4 cases. Okay? So how many probabilities do we need from the data, how many parameters, or how many probabilities do we need to determine for this edge right here? Anybody? 손. Very good. Why? Why is it only, I said 4 things, but he said only 2. Why? Because, can you say it? Okay, so I think this is what he's saying. Let's say you're intelligent, okay, so the conditional probability 1, and you need to, you define a probability for lots of time, okay, so 1, 1. If you know that probability, you also know the probability of intelligent and not spending more time, because it's going to be 1 minus that. Okay? Did you understand what I said? This is all I'm saying. I'm just saying. Probability of 0 given 1 is equal to 1 minus the probability of 1, 1. That's all I'm saying. If I know this, I know that. So there were 4 cases. So if I know 2, then I can get all 4 because of probability. Okay? So that's 2. What about here? It involves, it's a conditional probability of the score given DTQ. How many do we need? Just a half, right? 8. And then it's also here 2. We only need to know 2. So this graph represents the joint probability of 6 random variables. 6 random variables. Okay. So, and they're all binary. How many parameters would we need if we didn't have this graph? How many parameters would we need if I didn't have this graph and I'm just, in general? It will be 2 to the 6 minus 1. Okay? 2 to the 6 minus 1. Why minus 1? Because they all had to add up to 1. 63 parameters. But with this graph, I only need 15. And so, when I was talking about this, when you notice this, I'm assuming that everything is connected to everything. This one is very specific. There are missing links. Missing links give you information. Okay, I'm going to stop here and continue on talking about Bayesian net and Markov random field next time.